In this second module, we are discussing nuclear physics and its applications. In this ninth video, we will continue discussing the transformation of a portion of nuclear binding energy into heat through the fission process. After following this video, you will know how fission is used and controlled inside nuclear power plants. Natural uranium is a mixture of only 0.7% uranium-235 and 99.3% uranium-238. Uranium-235 has a 5 times shorter lifetime than the other isotope, and the natural mixture therefore contains only a small fraction of uranium-235. Enriched uranium is a material in which the uranium-235 component has been increased by isotope separation. This separation uses a small difference in mass between the two isotopes to separate them, for example in a gas centrifuge filled with uranium fluoride. In these devices, rotation generates an enrichment of the light element towards the axis and the heavier element towards the periphery. The devices are used in parallel and in series to obtain the required quantities and the desired level of enrichment. Enriched uranium is a critical component of both civil and military applications. A nuclear bomb usually contains at least 85% of uranium-235, but a simple and ineffective weapon can already be obtained with a minimum of 20%. The International Atomic Energy Agency, IAEA, attempts to monitor and control the production and storage of fissile materials around the world. In the controlled environment of a nuclear reactor, the chain reaction with K roughly equal to 1 can be used as a sustained energy source. The reactor core contains fuel rods with a fissile material, control rods with a neutron absorber, and a moderator to reduce the neutron kinetic energy and thermalize them. Thermal neutrons incident on natural uranium are radiatively captured by uranium-238 and will then not cause fission. That's why one uses uranium enriched to 3 to 5% of uranium-235 as fuel in nuclear reactors. The control rods in a reactor regulate the neutron rate. They are often made of cadmium, which has a high cross-section for neutron absorption. By inserting or removing the rods, one manages the flow of neutrons and therefore the reaction rate to keep K close to 1 and therefore a constant power source. The role of the moderator, on the other hand, is to slow down neutrons by scattering to increase their probability of capture and therefore increase the fission rate. A material with small absorption cross-section is chosen. Water, H2O, is used in light water reactors often found in Western countries. In research reactors designed to produce a large flux of neutrons, one also uses heavy water, D2O, because the cross-section for neutron capture is smaller in deuterium than it is in hydrogen. In reactors of the RBMK type, like the Chernobyl nuclear power plant, graphite moderation rods are used in addition to water. In a nuclear power plant, the reactor core is immersed in a cooling liquid, actually water. Its goal is to collect the heat generated by the core. Through a heat exchanger, the cooling water is used to produce steam, which will in turn drive turbines to generate electricity. At the exit of the turbines, the steam is condensed and recycled. The residual heat is often removed through cooling powers or dumped into rivers. The second goal of the coolant is to keep the core temperature under control and prevent the meltdown of the core. The whole is surrounded by a containment building, the small roundish building on the left of this picture, in order to avoid contamination of the environment by radiation. At the beginning of an exploitation cycle, the value of K is set to slightly above 1 until the desired power level is reached, and at this point K will be reduced to 1 to have a stable power source. We already calculated the impressive maximum energy yield related to nuclear fission. Ignoring the efficiency of power plants and other losses, 1 gram of uranium is equivalent to 3 tons of coal in heat output. This explains the important usage of this energy source in developed countries. On March 31, 2014, 435 reactors shown in this map were operating in 31 countries, with a total installed capacity of 372 gigawatt net. 72 reactors were under construction. In 2012, about 10% of the global electrical energy was produced by nuclear power. However, most nuclear reactors today are over 20 years old. The economic crisis in 2008 and the Fukushima nuclear accident caused a decrease in production of nuclear electricity by about 4% in 2011 compared to 2010. Countries such as Germany, Belgium, Switzerland and Taiwan have announced the end of their usage of nuclear power. Other countries no longer engage in new nuclear power plants. According to Wikipedia, the construction of 18 reactors appears several years late at this time. 9 are under construction since more than 20 years. However, the fight against global warming and the necessary reduction of fossil fuels may change the impression that nuclear fission is a power source in decline. In the next video, we will present the principles of nuclear fusion as a source of heat and see how it works in stars and in future power plants.